So I believe that you are all fine and kept safe. Welcome to another lesson whereby we are continuing with the topic in physics called the quantity of heat. Earlier on we discussed the terms heat capacity, specific heat capacity. Then we went further now to discuss, after knowing how they are calculated, we went further to discuss how specific heat capacity can be determined experimentally. Though some substances have specific heat capacities as constants and they are known, we can determine these specific heat capacities experimentally. Therefore, we discussed the electrical method of determining specific heat capacity. We discussed the method of mixing specific heat capacities. And in this lesson, I'll be bringing the continuous flow method of determining specific heat capacity of substances. So for this method of determining specific heat capacities, let me first of all record the apparatus you require for the experiment. Then we will see how the apparatus are arranged. We check out the procedure, we analyze the results and see how they can be manipulated to give us the specific heat capacities of a given substance. So what you require is you first require a constant head tank. I will show you what that one is. You also require thermometers. Yeah, only two. You also require a heater coil. A heater. Let me write on this other side. You require a heater coil. You also require a stopwatch, yeah? A glass tube is very necessary, surrounded by, or which has been evacuated, or surrounded by an evacuated substance, coated with an evacuated surface, coated with an evacuated material. Yeah, when you hear evacuation, you know that that's an empty space or a vacuum. That means that loss will not be through conduction and convection. Therefore, we now use an evacuated material to cover the glass tube so that we reduce heat losses to the surroundings. Yeah, so you can arrange the apparatus as shown. A rheostat is also important here. Yeah, I've recorded it. A rheostat. Arrange the apparatus as shown. Arrange the apparatus as shown. So you can have the constant head tank. The constant head tank. So this is an outlet pipe where some water can first of all flow out. Then after that, now, after water reaches this level, you now start the experiment. So what we have is now the heater. The heater coil now. The heater coil. Then we are having an outlet pipe here. elongate it so that it may not bring complications. This is a beaker. It's a beaker or a collecting vessel which will collect the water which will flow. So here, this is the heater coil, and you will have the two thermometers now here. Thermometer here and a thermometer here. So we have this one as thermometers. These are the thermometers. Each is a thermometer there. We have the glass tube here. Then we have an outlet pipe. It's an outlet pipe. This is the constant head tank. The constant head tank is there. Therefore, the heating coil is connected to a source of power. The van ammeter. Then a voltmeter is connected across. It should be across. Should be here across. So a voltmeter is connected there with an ammeter here. So the stopwatch you are holding. So now the procedure here, when you set up the apparatus like that, you can first of all allow water to flow from the constant head tank. Allow water to flow from the constant head tank as you switch on the current. As you switch on the current, let the water flow until the thermometers record a steady temperature. Therefore, initially, the thermometers, this thermometer can be having a biased readings because of the environment. But now when water flows for some time, you find now after some time this thermometer will be recording the temperature at which water is entering it. So we have water here flowing, we have water here flowing. Yeah, let me draw water. The water has been drawn. So we have water drawn, it is going through an heating coil. Therefore, the other thermometer will be taking the water temperature as it exits. So now, once the thermometers record a steady temperature, place a collecting vessel below the outlet pipe for the outlet pipe, and start timing or start the stopwatch. Start timing as you record some water here. record also the voltage and the current. The voltage and the current. Record the voltage and current. After some time, stop timing as you withdraw the collecting vessel. As you withdraw the collecting vessel. Then now after that you can repeat the procedure. Repeat the procedure for a different or with a different rate of water. With a different rate of flow. With a different rate of flow, you repeat the procedure. So let me just assemble the results here. The results and the calculations. So for the first rate, for the first flow, we can have ammeter reading. The ammeter reading has current 1, not A1. The ammeter reading can have it as A current 1, yeah. A1. Then voltmeter reading, or the voltage, is V1. Then time taken. Time taken, can have it as T. Time taken, you can have it as T. Then now here, we can have mass of beaker, the collecting vessel, mass of the collecting vessel is M1, and mass of water and the collecting vessel together. The collecting vessel together is M2. This implying that now mass of the water alone now will measure when you subtract the two masses. You get the mass of the water in this case. The mass of the water. It's good to know that heat lost to the environment or to the surrounding, you can call it capital H. The heat lost to the surrounding, capital H. Then for the second rate, or just at this level, you can say now that heat supplied by the heater coil is equal to heat absorbed by the water plus heat lost to the surrounding. Heat lost to the surrounding. Therefore, heat supplied by the heater coil be given by the power VI times time, which will be equal to, the first power to be V1 current 1 is equal to heat absorbed by the water, which will be mass of the water, times specific heat capacity of water times the change in temperature. Therefore, here we didn't mention that once the thermometers record a steady temperature, place a collecting vessel below the outlet pipe and start timing now. So, as you start timing, remember also to, as you start timing, very key step, record the temperature. Record, let me just write it, record the temperature or the thermometer reading for both cases. So the temperature of the incoming water, and of the water flowing out. Therefore, you'll be having, remember there are two thermometers. We have a thermometer, and after water has been heated, we take the temperature again with another thermometer. Therefore, you'll be taking the incoming water's temperature and the flowing out water's temperature. That's why we have liter 1 and liter 2. So temperature for the incoming water. Temperature for the incoming water. So temperature for incoming water, you can have it as liter 1, and temperature for the flowing out water, liter 2. Therefore, change in temperature will be liter 1 and liter 2 subtracted, plus the heat lost to the surrounding, plus the heat lost to the surrounding. So we have this heat supplied by the heater being equal to the heat absorbed by the water plus heat lost to the surrounding. Second rate. For the second rate of law, so what will differ mostly here is maybe the current being supplied because it just maybe reduced, and the water which will have been collected within the same time. Therefore, after time t, which is equal to the time for the first rate, then we will have a mass of water collected. Mass of water collected as M3. Mass of water collected as M3, or a mass of water collected and the beaker, because the water collected cannot be determined alone, and the beaker together is M3. And now here we'll say mass of water now in this second flow will be M3 minus M1 when beaker was empty. When beaker was empty. Heat lost to the surrounding will still be the same. Heat lost to the surrounding. Heat lost to the surrounding. Lost to the surrounding will still be capital H. Therefore, we say for the second rate now, heat lost, supplied, sorry, not lost, heat supplied by the electric heater coil will be equal to heat gained by water, heat absorbed or gained by the water, plus heat lost to the surrounding. Heat lost to the surrounding. Therefore here we shall have now current 2 and voltage 2 times is equal to heat gained by water, which will be now mass minus the empty beaker times specific heat capacity of water times specific heat capacity of water times change in temperature. So the first minus the second reading of the thermometer, then plus heat lost to the surrounding. Now because the heat lost to the surrounding is the same, then we can subtract these two, the first one and the second one. Therefore we can subtract, because the heat lost to the surrounding is just the same, we can have the two equations now subtracted. Therefore we shall have V2 current 2 T minus V1 current 1 times T being equal to this expression minus this one. Therefore you'll find it is M3 minus M1 minus M2 minus M1, then all now into specific heat capacity, specific heat capacity times specific heat capacity times the change in temperature, specific heat capacity times change in temperature, because it will remain the same. Specific heat capacity is just the same and the change in temperature is just theta 1 minus theta 2, but these masses are different. These masses are different. Therefore to get now specific heat capacity, to remain with specific heat capacity, of course of water, it will be here, you can see T is common, therefore we can have V2 I2 minus V1 I1 into T, then all divide by mass 3 minus mass 1 into mass 2 minus mass 1, then times change in temperature, times change in temperature. Therefore this expression is what will help us arrive at the specific heat capacity of water. This method has some advantages over the other methods we had discussed earlier, and one of the methods is that the method does not involve the specific heat capacity of the apparatus. The specific heat capacity of the apparatus is not associated in the calculation of the specific heat capacity of water. Another advantage is that heat loss by conduction and convection is minimized or reduced by the vacuum, the evacuated glass tube. And again, the method of continuous flow can be used for gases. It can be used for gases. So this method can be used for gases, unlike the other methods where we could only measure or determine the specific heat capacity of solids and liquids. The continuous flow method can also be used to determine the specific heat capacity of gases. So that is the method called the flow rate. In the next class, I will now be submitting the change of state, how materials change to gas from a liquid to liquid from a gas, and vice versa, and whatever heat changes are involved in the processes. So thank you very much for following us. I can wish you nice day, be safe, God bless you. Kindly subscribe to Shifting Grades.